1 year before. He was also visiting us sometime before. Eduardo did his PhD in Rio de Janeiro, the Catholic University of Rio, under the supervision of and he was working on different aspects of population dynamics, beta populations, effects of stochastic perturbations, nonlinear diffusion, pattern formation in biological populations. And he has been working also in this type of topics since this year. And he will show one of the purpose of the techniques mixing population dynamics with some evolutionary dynamics and spatial dependence in great operating systems.
Thank you. So thank you everybody for coming today. I hope you enjoyed this presentation. This is some interesting results that we got here at IFISC. Together, this work I've been doing together with Gustavo and Emilio here, and together with Ricardo. I think many of you know him. And we studied this interesting problem, which I'm going to first give you some general overview of what the scenario is, and after that I will show you, let's say, a more formalized outline of the presentation. So when you try to describe an ecosystem, you are going to identify many species there, you're going to identify many types of interaction, and you can construct this using the network formalism, and you can establish how a species relate between them. And one of the main interaction that there is the predator-prey interaction. This interaction is one of the main ones because is the one that promote the flow of energy from the lower bottom layers to the upper one. So there is a flow of energy in the system. And it is this type of interaction that makes this flow go to the upper layers. So this is just some sort of examples that occur in nature. So the one that I'm going to talk about is this one. This is just a nice picture of some predators trying to hunt a prey. They can do like very sophisticated stuff. They can collaborate together to hunt this animal. I don't know, I encourage you watching this documentary that I've been watching recently. It's very nice. You can find good examples of nice high definition recording in the field. You can see beautiful images and see the behavior of animals around the globe. So, of course, this fight, this pursuit that occur in the geometrical space, let's say a predator trying to hunt them in this geometrical space, it also occurs in the phenotype space. So this is a very interesting example that you can see a bat here and a moth. The bats try to detect the moth with sonar. They make these pulses to do like a sonar, try to find them. And of course the bats will be driven to have some nice sonar, let's say, a sonar that is enough to find moths around. But the moths will also will be forced to evolve to develop mechanisms that will try to avoid this detection. For instance, in this case, the moth do like some dance with the wings, trying to jam the sonar of the bat. So the moth will try to avoid this detection by scattering the sonar pulses. So this is one example. Another example is this hide and seek game. So I really can see if we can try. So there are some animals here. So there's one here, and they develop this type of camouflage to avoid detection of the predators. So this is one very key ingredient, because this is what sets the encounter rate between predator and prey. If the predator do not detect the prey, you do not have interaction. So a main property of this interaction is the range of which the predator can detect the prey. So this can happen by sound, view, tactile, or many other sensory mechanisms that you can imagine. So there is some eagle flying over Paris here, the bat and the moth, and some spiders in a web. And so this is I hope you interpret this as a nice joke, because if you are a predator and you are trying to, let's say, take a photo of your prey, and you can use a different type of lens, right? So if you're a predator trying to see something that is very near, you're just going to use these cheap ones, very small ones that you can just buy for a low cost. You have a low cost for finding them. But when you try to see something very far, or let's say when taking photos in a football match, you need something bigger, right? But there is a correlation between quality and cost. So when you try to see more, there is a cost involved in this. And if you go to the extreme limit, you want to see very far, you can build something with 40 meters, which have a very high cost. Weight and price and cost of energy to work. So this sounds a little bit absurd because we know that predators do not need to see too much. But there will exist some optimal range that is ideal for the predators. So this is what I'm saying. The perception range needs to be large enough such that the predator can detect something. So if the perception range is too small, no prey will detect it. But of course there is a cost involved, so there is this optimal value here. But as I was trying to imply, this optimal value is related to what scenario do you have. So if you are a predator and you are in this situation, predators here are the bad guys, the red ones, and the prey are the good ones, let's say the passive ones. So if you are in this scenario, if you are a predator here and you have a small perception range, you're not going to see anything. You're just going to see predators around you. And you are forced to have some larger perceptual range to detect something, even that comes with an extra cost. In this case, when the population is well mixed, you have prey moving around you very easily, so you don't need to have this large perception range. You can have a small one, and you don't need to pay this extra cost. So this optimal perception range is a function of this spatial distribution. So this is the first link that I would like you to pay attention. So this is the ecological driver of the trait of the predator. So this is the ecological part, and this ecological factor will drive the traits of the predator. But of course, the trait here is the perceptual range, and the perceptual range we use to eat prey. So this will affect the spatial distribution of prey and predator around. So there is a feedback between them. So when this ecological factor is trying to drive the evolutionary path, this evolutionary path will feed back to the spatial distribution. So there is an intrinsic coupling between them. And as I said, this spatial interaction and this encounter event will define the level of interaction that is present. So this will set the coexistence of this interaction. And this is, let's say, where I'd like to arrive in the final of the presentation. So this is the outline. I will try to follow more or less some order now. So yeah, I'll give you some introduction, talk about some motivations that can make you interested in this type of topics. And I will discuss this first one-way direction where the ecology drives evolution, and discuss a little bit about habitat changes and how this will affect the system, and how evolution can play a role in these times of changes in the environment. And of course, I will mention some examples of evolutionary feedbacks that is already reported in the literature. And at the end, I will discuss our problem, discuss this eco-evolutionary feedback that occur in space among these spatial scales, and discuss some other properties of the system. So this is the let's say the common sense scenario. So you have a fitness landscape. So you can imagine that this is typically a very high dimensional space, but you can imagine two traits of an individual. Let's say the size and the color. So there will be a certain size and color that will match, that will give maximum success to this individual in the environment. And what you imagine typically is that this landscape is set by the ecological factors, let's say the environment, the landscape, and the climate there. So the population do not play a role in these external constraints. The external constraints are given, and the population will, with the time, will evolve to this optimal scenario here. Of course, in reality, you can have some more complicated landscapes in the fitness space. So when environment changes, there's a change in environment, this fitness landscape will be affected. So, and today, recently, this becomes really important because human activity has been changing the environment in a very fast pace. So new habitats are emerging, such as in urban areas. So this is London. You can see the Thames River here, and the greener regions here are the ones that have, like, say, parks and vegetation around. So the population that live in the city need to learn how to live in this fragmented situation. And fragmentation and degradation of the environment also happen due to deforestation, let's say in Amazon forest, And this is just an example in the United States how the Greenland has been reduced with time. So not only human activity affect the habitat by changing the spatial structure of it and other things, it's in a general way the human footprint in the environment affects animal behavior. So this footprint can be quantified by means of, let's say, presence of cars, pollution, buildings around, and you can quantify this human footprint index. So it has been shown, for instance, that the animal mobility, so the median displacement of, I think it's mammals here, decrease with human footprint. So mobility is decreasing as human impact increases. Mobility decreases as human impact increases. So this is a very dark way to welcome you to this Anthropocene era now, where things are really bad, and many people are saying this, not me, of course. Some important ecologists just they wrote a report recently. I think it was 1 month ago. It was released, and they try to help governments what we need to do to save some species that are in an accelerating rate of extinction. So, and one of the major causes that they point out is a need in the change in the land and sea use. I think this is also related to the Posidonia problem maybe here, that boats remove the seagrass and affect and maybe put some plants in a dangerous situation. So this is the scenario. So that I was wishing to arrive now. So you have the population in a certain stationary state or quasi-stationary state, and suddenly there is a habitat loss in the system. So when this loss happens, the population will be optimized to the past situation. So the environment changes, but the population do not change because the evolution do not have time to do it at this point. So there is a lag between environment and population state. So this creates this concept of extinction depth. So the individuals that are living there now, the species that are there now, are fated to die at some point because they are suboptimal to the environment that they are living in. So, and after some time, of course, the system can relax and adapt to the new scenario. And it's interesting that if the species and if the evolution can happen in comparable timescales, evolution can come to the rescue and maybe perhaps save the population to a certain drastic situation. So this is a case study for a certain type of plant, and you can see here this is the time, and this is the occupancy of the habitat. So the black line is without evolution, and when evolution is there, the habitat becomes more occupied in the long time. So evolution helped the system to become more persistent. So I will talk about now some other examples and eco-evolutionary feedbacks. So this is the classical case of hair in lynx. So these cycles, you can see the times here is the traditional, the classical case. And you expect to observe this type of counterclockwise cycles. So when prey abundance increases, this will promote the increase of predators, and you go this way. So when the predator population is very high, the number of prey will decrease. So you expect this type of cycles in this space. But some people, Cortez reported here in this case that if you have coevolution of the offense and defense mechanisms of the predators and prey, you can revert the direction of these cycles, making it clockwise, which is a bit strange. And also, if you have a genetic variability in the population, this will affect the period of the cycles. So this type of feedbacks interfere in the cycles, interfere in the persistence of the population, as I showed before. And some other examples, this discussion has started of course, some time ago. And on the 2000s, there are some nice works pointing out the importance of evolution in ecological aspects of the system. And there is a recent, let's say, a review about the topic, which I recommend you reading if you want to go further here. So now it starts the topic that I'd like to discuss. And the things that we're going to study is spatial dynamics, because the spatial dynamics is one of the key ingredients of interaction here. So this is the model, and I'm going to be more concrete now. So the model is very simple. There is no any fancy things here. So we have preys reproducing with constant rate. We have predators dying with constant rate, but prey death and predator reproduction are conditioned to the interaction between them. So when there is an interaction between them, which occurs with certain rates, of course a function of the perceptual range, a prey will die, and with a certain probability, a newborn predator can be generated. So there is a probability that the prey consumed will be converted in a new predator in the system. So here we chose to model the catching rate as a function of the number of preys that the predator have around him. So with this factor that take account the efficiency, which will include the trade-off between the cost that a large perception range have. So this is the figure that I showed you before. So when you increase the perception range, there is a component that increases with R. So that's the number of preys being detected, but the cost is here. We just set an exponential for simplicity. And mutations, of course, when you generate a new predator, the new predator will have the traits of the parent plus a noise. And this noise is like a zero mean Gaussian white noise with variance sigma mu, which regulates intensity. So every clonal, every newborn that arrives in the system have some defects, let's say. And the intensity of these defects is given by the sigma. So the copies are not perfect, and the level of imperfection is given by the sigma. And also dispersal. Every individual do like a Brownian motion with different diffusion coefficient. Actually, it is the same for predators. This is the preys, the prey diffusion coefficient and the predator diffusion coefficient. They are the same for all individuals in the same species. So this is the model, and we implement this following this prescription, maybe known as a Gillespie implementation or Gillespie prescription, which assumes that these events are Poisson events, and you can implement, like, let's say, in a suitable way that you can find good correspondence with microscopic equations, if you wish. So the model generates this time scale. So you have this time scale related to the cluster of predators, related to the cluster of preys, and of course the perception range. So this is the time scales that will interact. So, okay.
You have a interaction range between the predator and the prey. So we have go back.
Okay.
That P plus B only happen when P and B are at the process at some given distance, or?
Yeah. This interaction only happens when the preys are in reach, inside the.
So there is an interaction range also.
Yeah. It's the perception range. So when you can see it, you try to attack it if you want. So the first step that we need to make is to quantify this spatial structure in order to know how they are influencing the system. So this is the two scenarios, two extreme scenarios, so the high clusterization and almost well-mixed situation. And what we do here is to quantify how well-mixed the populations are. So we start dividing the space in grids. Of course, the size of the grids have some importance here, but you need to choose it well. And you can use this entropy ansatz, which will, let's say, give the level of disorder inside each cell. So if there are half of each species in one cell, you maximize this value. So this is the well-mixed case, so the mixing will be higher. But if there is only one species at one cell, this mixing will be zero, and there is certainty that there is only one species. So this is the situation that I was mentioning. So if you have half, there is a maximum value, and if you have just one of them or the other one, you give zero. So this is high mixing and low mixing. And there is a smart way to rescale this measure, because you actually don't want this measure to be an absolute value. You want the measure to be a relative value to the homogeneous case. You want to know how different from the homogeneous situation you are. So you can calculate the homogeneous mixing measure because you can do it analytically and divide it, and you can have some sort of nice things that is independent on the number of particles, independent on other details of the system. So this is the result when you increase, let's say, here I'm increasing both diffusion coefficients. All the praise and the predators are becoming faster here. And you come from a low mixing, so clusterization, to a well-mixed scenario. So I'm also showing here that individually, praise and predators are also becoming more spread in space. So this is just to show you. An interesting situation that you can analyze, you put now slow predators, so the predators are, let's say, relatively slow, and we increase the diffusion of the praise. So when you increase the diffusion of the praise will try to drive the predator population to a more homogeneous situations. So this will be this part here. So the predators will appear more randomly in space as prey population become more randomly distributed. But there is this goes until a certain point. Because when praise becomes too fast, predators will lag behind and become clustered again. So this is more or less, we are talking like a brown and coyote roadrunner, because the roadrunner is much faster than a coyote, and the coyote lag behind. Of course, here we do not have this following mechanism, but this is what happened in this scenario here. And this is illustrated by this experiment. So you put some bacteria, which you can interpret as the predator, and you can define a region where the resource is let's say, it's enough to promote growth of the population. So when this region, which have resources, that you can imagine that this region with resources is the region that have praise, for instance. So when this region moves in space, and it moves slow enough, the bacterial population can follow it, you see? So they are, let's say, well mixed. So they follow it. The direction diffusion process can make them go together. But when the movement of this region is too fast, the bacterial population lag behind and they become clustered again. So this is illustrated by this problem. So this is the nice movie of the simulations for the low mobility case. So you can see some bursts. So this is the predators are going around. I would like to focus now here. Where is it? Here. So the predators are here. You see that they are trying to follow this cluster. Now it divides and try to follow this one. And do you see, I'm using the word following, but it's not a following, because the predators that are in the interface between the clusters will have a higher probability of reproduction. So it's actually a reaction diffusion process. I can show you again. So, and it's interesting to see the burst, because when one predator finds a near prey population, there is a burst of reproduction. And you can see also the perceptual range change in time. So when you start the system with any initial conditions, the stationary regime is not affected. So when you have low mobility, you have the cluster situations, the perception range is larger, as I tried to imply in the beginning, because you need to see preys that are far away. But when you have a well-mixed scenario, the perception range can be smaller. So after this transient, the system arrived to a stationary, quasi-stationary state. I mean quasi-stationary because you have the probability of extinction, so it's not a... So this is a stationary state. You have the distribution of traits there. So this is the R star that I plot here. This is the mode. There's a wave propagation, right? So you start with the system will, the phenotype, there will be a phenotype wave that will propagate to the stationary solution. So you can see the different values here. So in general, the value of the mode, the most frequent trait in the predator population is a function of the degree of prey clusterization. So the predator perception range will increase with this prey clusterization factor here, as more or less as a power law. You can see this is the power law of it. Actually, there's no particular reason to be a power law, but it looks nice that way. And then, of course, when preys are homogeneous, so prey clusterization is zero, the dominant trait approach the one of the well-mixed case, and then it increases as prey clusterization goes on. For the well-mixed scenario, we could make some calculations. So this is the equation that drives the distribution of traits in the predator population. So you have this term which is related to who we reproduce. Which are the predators that have success in this environment, and they reproduce and generate newborns. But these newborns will have their traits spread in the phenotypes because of the mutations. So you have some sort of natural selection here and diffusion due to mutations. So this kernel here simply spread the newborns into new traits in the system. And for the homogeneous case, it's easy because we know the prey distribution and we can estimate the number of preys that are inside the predator perception range, which is simply the area of the perception, the circle of perception times the prey density. So the comparison of simulation in theory is very nice when of course the system is large, and you can obtain some nice comparison between them, and everything works well for this case. So this is, let's say, is a checkpoint in the presentation, because until now I'm just show you how the spatial distribution are imposing these new traits in the population. So mutation allow this relaxation to the stationary state that are suitable for the predators, and mutation also introduce variability in the system, and also here there is a small shift to larger values just because of details in the asymmetry of the trade-off. So, but more or less, I'm going to focus now in this capability of the mutation to promote this relaxation to a new stationary state and variability in the trait. So, okay, so this is some new results. What I just try to develop here a scenario that I motivated earlier. So imagine that everybody is well mixed, so all individuals have a high mobility. So mixing is very high. The perception range in the predator population is equal to 1. Actually, we scale here, so the dominant trait is the one responding to the well mixed scenario, and the survival probability during this initial transient here is 1. So the population have let's say 0 probability of extinction in this time. But suddenly in this t prime here, let's see 50 years, 50 seconds as we wish, something drastic will change. The individuals will reduce their mobility, maybe relating to the case that I showed earlier, due to the human impact or any drastic change that occur in the habitat. So animal mobility will suddenly be reduced. So when this happens, you can imagine that mixing will decrease, so species will become segregated. So when this happens, if you don't have evolution, so I'm going to show you 2 cases. So this one case, the solid line is a little bit high mutation rates and low mutation rates. So when this drastic change happens, if you have low mobility, the traits will be static. The population will not change, and it will happen as a suboptimal situation because the trait is not optimized for this new scenario that emerged. But if evolution timescales are short enough, you can see this adaptation of the population to this new scenario. So this is more or less related to the problem that I showed earlier. So evolution is coming to rescue. So evolution allow the population to optimize to this new scenario, and this is more or less represented here. This is the survival probability as a function of time for the low and high mutation cases. So you can see that for low mutation cases, due to the suboptimal scenario, the probability of survival is much lower when evolution can act and rescue the population, let's say. So you can have maybe a factor of 2 or more here to the survival probability of the population when evolution occur in a fast pace. So this is the first feature that I mentioned. This is relaxation, right? So, but there is also variability. When mutation is high, you have high variability in the predator trait and low mobility. So mutation rates are also affecting the variability in the population. It's very interesting to note that this variability is affecting the mixing. So this is the comeback. So when the variability is affected by the mutation rates, you can see that the changes in the mixing. So this is the relative change. So when you increase when you increase mutation rates, the mixing at low mobility is reduced, and the mixing at intermediate levels of mobility are increased. So the variability in the trait are affecting the mix. So this is the comeback, the feedback. So the traits, the evolutionary outcome is affecting the ecological part of the system. So this manifests in this very, actually, a little bit complicated plot. So this change in mixing here promotes this high coexistence times in this intermediate mobility. So this feedback, all this feedback is controlling where the population coexists longer. So, and you can see that the increase in the coexistence time at this point is related to the influence of variability in the mixing. So you see the feedback that the traits having mixing and this everything together affect coexistence because the interaction between predator and prey change. So I think I'm more or less finishing. I just would like to give you some final remarks. So of course variability in the population can be introduced not only by mutation, but variability can happen due to environmental factors. And it's more or less similar here, but variability evolution makes possible the system to adapt to new states. This is not created by just variability in the population. So this time scales that mutation allow the system to adapt and become resilient to environmental changes is an important difference between these two comparisons here. So, of course, there is an interesting topic because here we just studied one perceptual range and how these dynamics evolve. But of course, you can have a complete food web where there are many animals interacting there in a network like this, and has been shown that there is a scaling law in this type of food webs such that the predators that are larger are rare in the system, and the predators that the species that are smaller are more abundant in the system. And if you imagine that size and perception range is more or less related, that maybe there is an effect here, and this can play a role in this type of dynamics. Also, I didn't discuss here, but this is the plot for our problem. This is the probability of extinction of prey. So this is also affected by mutation rates. So at a long time, eventually predator or prey will become extinct. And this probability change with mutation rates. So this affects the diversity in the system if you have many copies of this problem that I showed you. Also, there is a nice analogy here because we just assume that our individuals are active, so they are moving by themselves with a certain diffusion coefficient, but they can be passive and be driven by external flows. So I borrowed this image by a work by Pedro, and this is some simulation of shear flow. So you can imagine that the problem that I mentioned can be related to turbulence in ocean. So this clusterization will occur when turbulence is low, and high mixing will occur when turbulence is high. So this is what I'd like to talk to you. I'd like to thank everybody that worked in this work, Gustavo, Emilio, and Ricardo that is not here. I'm happy to answer some questions, and thank you all for your attention.
Questions?
I have a question that I have not understood well. Some detail the role of this detection range.
Okay.
Some audience say, no, here, when you are presenting this movie, kind of movie, you say, here the detection rate is lower and it's higher.
Yeah.
So what is behind in making the detection range changes, and how is being controlled by the model?
The evolution of the perception range in the population is caused by evolutionary dynamics. So you have natural selection and mutation. So this is the only these two ingredients. So the predators that can catch prey, we don't know, let's say, the ones that can catch prey will reproduce and propagate the trait to the next generation. And happens that when you have clusterization, the predators that do this are the ones that have larger perceptual range.
So it's a feature within your model that is chosen randomly.
No, it's evolving.
It's evolving.
It's evolving because you have different success for each of them. So if you are a predator with, let's say, 0 perceptual range, you're not going to catch anyone. So you're not going to reproduce and propagate this to the next generation. But if you have the exact value, you're going to reproduce and generate a newborn more or less like you, with a small noise there.
And then evolution will make the detection rate increases or decreases?
Yeah, depending on the individual mobility. So there is this input from the individual level, which is the diffusion coefficient of the particles, and this will generate a macroscopic outcome, which is the spatial distribution of the species, and the traits will be a consequence of this.
More questions?
I cannot understand this ecological evolution
Feedback. Yeah.
Whatever. From my zero understanding in biology, the times necessary for evolutionary changes are very long. Right?
Yeah.
Why?
Sure.
For ecology, I think.
Yeah, that's the common sense, but that's not always true. So typically what we have in mind is this scenario that I show you early. Environment changes, but evolution is so slow that the population features will stay the same. But if evolution is fast enough, evolution will play a role, right? And this can happen. This can happen. This has been shown experimentally and theoretically. So this is a...
It depends on the species? Or
Sorry?
Depends on the species?
Yeah, of course, yeah. Of course, it's easier, for instance, for microbes and virus because the mutation rates are much higher. And for instance, if you compare to the human beings, the mutation rates are much lower. Yeah.
More questions? Any comment? If not, thank you.